On the previous video, we showed what was the data input from ELMER and we go through it. In this video, we're going to perform ELMER analysis with that data. So first, we have to define some parameters that are used in null functions. The first one is called group call, and it defines which is the column in the metadata that has my both two groups that are going to be compared. For our example call, it's called primary diagnosis, and we're going to compare two groups, the adenocarcinoma versus the squamous carcinoma, and those can be verified by the data I'm going to show later. And then you define in which direction ELMER is going to look. So are we going to look for the hypomethylation in group 1 or group 2? When you write hypo, it's always related to group 1, so it says, okay, I'm going to look for probes that are hypo in group 1, then which are the targets gene of those regions and transcription factor bind to those hypo in group 1. If you write hyper, it means you want the hypermethylated probes in group 1, so we're actually looking at the hypo probes in group 2. So the question is, which are the master regulator transcription factors regulating group 2. So we're going to use hypo, which means which are the mass regulators acting in group 1. Okay, and we set number of cores and supervised mode. So as I explained, since we know that adenocarcinoma has its homogeneous, should be homogeneous between all the samples, and also squamous should be homogeneous between them, we're going to use the supervised mode, which uses all samples. And also we need to set where's the directory where the data from the analysis is going to save. I normally use I use this code to write the directory, which is going to use the information from the group call we're using, which are the groups being compared, mode and direction. So we know actually what was the analysis we did. Okay, so just going back to the code, I'm going to run this information and just show the directory out. It's going to be analysis, primary diagnosis, group 1 versus group 2, supervised mode, and hypo. And just to show the data, like we said, if we set my, so we're using primary diagnosis, right? And we see here we should have 7-8 samples from adeno versus 7-6 from squamous. Okay, after you said that, we are going for our first ELMER step, which is identifying the hypomethylated distal probes in our adenocarcinoma samples. This is done by this function, get differential methylation, get diff meth. The parameters here, we set the data, which is the multi-assay experiment, the column in the metadata, the group 1 and group 2 we set. So everything that's not adenocarcinoma and squamous was going to be removed from the analysis. That's why we use those columns. Then we set the direction, so we want hypomethylated probes in ESAD samples in adenocarcinoma. The number of cores, the mode of the, if we're going to use supervised or unsupervised, and then the p-values and significant difference methylation. And then dir out, this should not be empty, should be the same we said before. So this is the first step. So dir out should be like this. It's probably fixed in the, yeah, this is, it should be fixed, but I'm going to fix later. Then it's going to give you several information about the run. So we're analyzing the same probes from the object that I showed before. We expect a difference of mean beta values of 0.3 and FDR 0.1, and we are using all samples from the from the data, and we have like 78 from group 1 and 76 from group 2, which was the same we have here. The output of this is going to be like a table. Let me see if I have here. Yeah, it's going to be like this. So we have probe, the p-value, the FTR, and also the mean difference between both groups. So since it's negative, it means the mean in the adenal is lower than squamous. So let's say it's 0.1 here and 0.5 in squamous. So squamous is hypermethylated. Basically, this is the output of this function. After you have the probes, you have to map those distal probes that normally they are enhancers. We need to check which is the gene, nearest gene being regulated. For that, we use the function get near genes. So we give the data, which are the probes, and then how many genes we want. One thing that it's important to say here, it's expected that your multi-assay experiment has all the genes, like the 56,000. Imagine you subset it and your expression inside the object has only 1,000 genes. The probes will somehow associate to those genes, and they might not be the real ones. So if your object does not have all the genes here, it's better to provide the list of all genes and the ranges of the probes. So that's how it's done. But to be easier, we have also this shortcut. And this we're going to have like for the same probe, all the genes that are linked, the distance between the TSS and the probe, and like how many genes are between the probe and that gene. So L10 means it's the most left one, then 9, then 8, and then the close ones are R1 and L1. So just to show the different methylated probes results, and that's what you got. Also, when you run this, you should have a Volcano Plot. So sometimes you don't know which would be the best cutoff, but you can see from the Volcano Plot where are the probes. Sometimes you, like if you're comparing two tumors and they don't have like this difference, you might sometimes just have a less stringent cutoff and maybe a less stringent p-value cutoff. Okay, so we're going to get the nearest genes. It's going to take a while again. And then the next step is, okay, we have our 10 genes, which is one being regulated. We look for an anti-correlation again, so it's hypomethylated here. And we expected that if it's active, so a transcription factor is binding in that hypomethylated region, that a distal gene is being upregulated. So that's what this next step is going to do. So again, we give the data, which are the near genes, so it's going to test all pairs. Again, the group call, group 1, group 2, the mode, direction again, cutoffs for the p-value. The difference between those two is this first one is going to be the cutoff when you compare these two, and the P is for the permutation. It's the one that's the p-value corrected. This is only used in the unsupervised mode. In the supervised mode, it's also going to use this, but it's going to be the cutoff for the FTR. And then we have this function here, which has 3 arguments, which is a filter. So you said if you do want to filter the probes or not. So there is a binary clusterization of probes. We expect that each probe has at least 5% of samples with values below 0.3 and 5% with values higher than 0.3, which is set by this. So this sets like the portion. So 0.3 is going to be the binary distribution. So say, okay, how many samples are below 0.3? How many samples are above 0.3? Okay, are they 5% in both groups? Yes, so we keep that probe. More or less, that's the main arguments of that function. This is the step that might take more time while running ELMER. In the unsupervised mode, the supervised should be pretty fast. And yeah, just to show from the 148 probes, 100 probes does not have this distribution, and then within those, the rest of them, we get the differential methylated ones, and we see which ones are within. Those are the ones being tested. So again, my dear out was hypo. So just to show analysis, right? Just to show that the results are being written. You should have several spreadsheets here. So these were the last files created. You have all the pair significance statistics. So just to show, you can click it on RStudio, and then it should open here a preview of the data. So this is all pairs. So all. Let me see if it's going to take a while or not. Otherwise, I'm going to open one that's less bigger. Yeah, let me get one that's a little bit smaller. Yeah, this one. Yeah, so you should have this probe, gene ID, gene symbol, distance between them, the same information from the get nearest genes, and then the ROPI value and the FTR between them, or the permutation correction if it's unsupervised mode. So we should have by this time 5,000 pairs, okay? And then our question is, okay, which is the master regulator transcription factor binding to those hypomethylated regions? And then we have two functions that I'm going to show you later. So so far, if you want to visualize the pairs, you can use this function, hitmap pairs. Give again the same information we provided before, and then the pairs we want to plot. This function takes a lot of time to plot, so we're going to just plot the 100 one. But this is more or less what we're expecting. So we are looking for hypomethylated samples in adenocarcinoma. So adenocarcinoma is light blue, and the gene are upregulated, while the squamous is hypermethylated and the gene is downregulated. So this anticorrelation. Yeah. So blue means hypo, yellow means close to one's hyper, and the z-score, and then the expression is mainly z-score. The z-score is actually the value centered. So you get the median value and set to 0, and then all the other values are going to be the distance between that center. We use that for gene expression just to be easier to visualize that in a heat map, because we might have cases where the gene is super expressed in all samples. I don't know, like 1,000 counts, and the other one's low expressed. And if you don't do the z-score, it's going to be difficult to visualize the difference between the expression of each gene for each sample. Okay, so the next function is get my enriched motifs on those hypomethylated regions. Again, you set the data, you use that using the get enriched motif. You set the data, which were the probes that are hypomethylated and has a gene associated with it. So you get the probes from the pairs. We set unique here because we don't want to repeat probes. I believe inside the code we already do that, but it's a good thing to do outside. And then we want to say that the enriched motif needs to have at least 10 probes, and the lower odds ratio has to be at least 1.5.